Hello everyone, today we'll talk about the problem open the lock. We're given a combination lock consisting of 4 wheels. Each wheel can show us numbers, digits between 0 and 9. We're given a target, so the 4 digits that are the password to this lock. We start at all zeros, and one monkey wrench in the works, so to speak, is the fact that there are some dead ends, some combinations, not including our target, that if we reach them by trying to turn some wheel, then we can do nothing else. This is something that we want to avoid because it locks up the lock and we cannot turn it anymore. We essentially pay 1, so spend, let's say, a second to rotate any wheel either in one direction or another direction by 1 step, and we have to say how few turns are enough to reach target from all zeros, or -1 if it's impossible. And one way in which it can be impossible is if we have a target combination such that any of the 8 combinations that can be got from it by rotating any wheel up or down, so there are 8 options, if they are all dead ends and we are not starting at target, then of course it's impossible to reach target because our final move would have to turn one of those wheels from a position that's next to the given position in target to the correct position, and all of those combinations are at the list of dead ends. So it's possible for it to be impossible to reach the target. Now, if there were no dead ends, then the answer would be simple, because we could just think about every wheel separately. There are only 2 options. We either turn it enough upwards or turn it enough downwards. We can take the minimum of those required moves and then we reach target. But of course there are these dead ends. One thing that we may want to do is to try to avoid these dead ends, but probably the easiest solution here is to notice that the number of all the combinations, of course, there are 4 choices, so it's something to the power of 4, and that something is the number of digits we have. So it's 10. So there are 10 to the 4 combinations, and that is not a very large number. In particular, if we can devise an algorithm that works in linear time with respect to this one. So for instance, we notice that there are 10 to the 4 combinations, and from every combination there are exactly 8 moves that we can make, because we can turn the first wheel up or down, the second wheel up or down, so there are essentially 8. So we have 8 times 10 to the 4 transitions from those 10 to the 4 states. And this is a graph that's actually simple to traverse. And the only thing that we need here is to find the shortest path from start to target that doesn't visit any of the dead ends, so we can just not include our dead ends in our graph. And since the edges are not weighted here, all of them have the weight 1, then you can do it with a simple BFS, with a simple breadth first search. So to recap, the first step is generate all those options. The second step is subtract dead ends. Third step is add edges. And step 4 is BFS from 0, 0. I will also use this opportunity when showing you the code to show you perhaps some of quite simple but still tricks that you can use in Python that make Python a popular language for many people. Okay. So, first we can check if target is the starting position, and then we have to only turn the wheels 0 times, so we might as well get that over with at the beginning. Then we have to get all our options. So those are all the positions that are not dead ends. And let's first generate all the positions. Those positions are a Cartesian product of all the digits taken 4 times. And since we write in Python, we have in string the variable digits, which is digits from 0 to 9 as a string. If we want that Cartesian product of digits with itself, we use product from iter tools. And since we want it 4 times, we write repeat equals 4. And that's all that we need to do. Of course, in LeetCode, those things are already imported. Otherwise, you would have to write import from string those digits, from itertools this product. That will give us a list or tuple, I'm not sure. And we want a string, so we have to convert it into a string. How do we convert a list or tuple into a string? With join. We join it without adding anything between them. So this is an empty string, dot join, and that will convert the list into a string. And now we want to do that for everything in that product. And to do so, we can use a map. And notice that this is a bit of a functional programming, let's say, because typically when you have a function, of course, you would write here that you call it, but we don't want to call it, we want to only get the function, and map will call it for us for everything in this product. And then we want to, of course, not have any duplicates. There are no duplicates, that doesn't matter. But we might as well also convert it into a set for the next step. And the next step is to remove all the dead ends. And we could do it, perhaps we could do it by sorting. That would be simple. We would have to sort this first list, sort this second list. And then we indeed can remove all those bad dead ends. First we would have probably to mark all of them and then to remove them from the list. But we might also just consider the fact that in Python we can subtract sets from each other. And in that way we have a set that doesn't include any dead ends. Okay, so now we have all our options. Then we have to create our transitions, our edges. So for every option, we will try to turn every digit up or down by 1. So we prepare them as a list. Then we will be turning it back into a string and adding it as a neighbor. And of course, if we're writing in C++, then it would be simple arithmetic on characters. We can just subtract 1, and if necessary, add 10, or add 1, if necessary, subtract 10. So that would be the same as modulo, and of course it would be faster to just subtract or add. Because so essentially if you have, let's say, the digit 9, if you add 1, then you get some other character that is, I'm not sure if it starts at 0. Anyway, if you want to get back to where you were before, then you would just have to subtract 10. Of course, you would have to know how those digits are positioned, but we're not going to do that here. We're going to just take our digits. We can zip the digits with our digits offset by 1. And since this is 1 shorter, we can either, for the last digit, write that it comes back to the first digit, so 9 comes to 0. But we might also just add all the other digits to this one. So essentially, this is going to start at 1, 2, so on, until we reach 9, and then it is 0, 1, and so on. And this digits is 0, 1, up to 9, right? And we do it from left to right. This is one direction, and from right to left, it's another direction. And in that way, we just take the next digit, we go in one direction, add it as a neighbor, go in another direction, add it as a neighbor, and we restore the old digit. Now notice that we may add a dead end as a neighbor, but it doesn't matter because since we do it only for our options, so we have already subtracted all the dead ends, then they will literally be dead ends. There will have no outcoming edges. And now our graph is ready. The only thing we need to do now is to run a BFS. So we'll keep an information for what positions were already visited. We can use a set for that. We'll have a queue, which in Python you just use a double-ended queue, not the queue module, because that module is essentially for synchronizing, and it's not a simple data structure like a double-ended queue, like a deck. And one way I like to write BFS is like this. We will of course take everything from the queue, so we will pop left, so take the first element, we will append to the right. This is how you write it for a deck. And we somehow have to keep the number of steps that we have taken. One way to do so would be to not keep only the position on our queue, but also the length of our current path, so the distance from our starting node. But notice that it's not necessary. We can, instead of just going through all the elements of the queue, we can consider big blocks where we work on every element that is at a given distance at once. So now that we have finished, this is the first block, or we have finished the previous block, we remember how many elements are currently on the queue, because their direction will be one more than before. We increment that direction, and then we go through all those elements, and we know that this is their distance is exactly these steps that we incremented. And of course, if you want to write this simple way, like in C++, that you assign in the while condition, you can use this so-called walrus operation. If we write s colon equals length of our queue, then this will give the variable s the value of len q. So this is like we would write that in C++. And then we just go through the s elements in our queue, because we know the distance for them. And for every neighbor in our graph that we have created, if it's not visited, then of course if it's visited, we don't do anything. Otherwise, if it's the target, then we know the distance to the target, so we stop early. Otherwise, we just add it as visited and add it to our queue. And if the queue is now empty and we haven't seen the target, we return -1 because it's impossible.